All right, everybody. Good morning. Let's keep going. It's right at 11, and people are coming in. All right, we are in the final 2 weeks, so we have 4 sessions together. This morning, I want to talk about what's covered in Chapter 9, which is soil and land degradation. And then on Thursday, I will introduce you to water quality and water resource issues. We'll carry that through to next Tuesday, and the next Thursday will be the wrap-up. By next Tuesday, I will have the study guide out for the final, and I will talk more about the final next week. But let me just make one request, and that is, if you need to chat before that final, things start really getting packed together, and you folks know that, right? You've got a lot coming at you in these next 2.5 weeks. So please budget your time, and my calendar will start filling up pretty quickly as from next week. Just send me an email if you want to talk about anything relating to the final, your grades, whatever the case may be, and I'll slot you in from there, right? Any questions on the logistics before we move forward? Anybody got any questions or concerns? I've heard from 3 of the graduating seniors. So if you're a graduating senior and you haven't emailed me, please do, because we need to set up your final exam ahead of time. All good. Okay. All right. So let's talk about land and soil degradation. And I know to a lot of people, this probably doesn't seem like an especially important, perhaps, or controversial topic. I think a lot of people think, well, now we're going to talk about dirt. Okay, so what's the concern with that? Well, the concern is that this is arguably our most important resource, right? I mean, oil is great. Energy is important, all the things we've talked about. But if we don't have the medium in which we can grow food, then we are in serious trouble, right? So soil and land degradation, I'll clarify what those 2 terms mean in just a little bit, right? So I'm fine if you want to call it dirt, but it is incredibly important. And President Roosevelt recognized that during his presidency. Just a short quote from a speech that he made related to agriculture and farming: a nation that destroys its soil destroys itself, right? And I think maybe we don't think about soil as the critical resource that is under threat, but I hope to make the case that in fact it is. Now, soil fulfills a variety of functions, and I've tried to summarize those functions in this diagram here. Clearly, the top left one is critical, right? It's the medium for plant growth. So it's the medium in which we grow crops, for example. But it does a whole bunch of other things. And like a lot of our environment, it does these things for free, right? So it is the medium in which nutrients and wastes are recycled. Healthy soil is absolutely vital in terms of water quality. It's also, of course, an engineering medium. The soil is a multi-purpose physical resource. We tend to focus on the top left one, I think, more than anything, right? What does soil degradation mean for agriculture? Probably more than anything else. From a book called The Secret Life of Soil. If you're desperately interested in soil and you want some bedtime reading, let me know. I can put you onto The Secret Life of Soil. Healthy soil is a jungle of voracious creatures eating and pooping and reproducing their way towards glorious soil fertility. I think it's not really appreciated just how vibrant soil is. So, for example, a single teaspoon contains, something like 1 billion bacteria and several yards of fungal elements and so on, right? So even what looks like it might be a reasonably sort of lifeless lump of soil sitting on a teaspoon is, for the most part, extremely rich. So that's the kind of outcome, the take-home message for today, right? Before we get into some details here, is that this really is a resource that we have to pay immediate and very close attention to. And just incidentally, the first sort of, I don't know, 15, maybe even 20 years of my research career was focused on soil quality, soil degradation, land conservation, and so on. So this is another area that is particularly close to my heart. Okay, so before we get to talk about soil degradation, let me just introduce you to the very basics of soil science. And this diagram here is important. You'll get to see this diagram undoubtedly on exam number 3, on the final exam. And the reason is I want you to be familiar with the 6 major soil horizons. Okay, let me just, oops, I think I've lost my mouse. No, I haven't. Let me just pull up the chat there. Okay, so these 6 horizons are the key soil horizons. I want you to be able to talk very, very briefly about each one and give, for example, a distinguishing characteristic of each. Let me say that all 6, you almost, I'm trying to think off the top of my head, but I can't think of one, of a situation where you would find all 6 together, right? These 6 horizons mean something. So when you dig a soil pit, or when you drive down a highway and you see a road cut, and you see these different horizons that generally we tend to notice first in terms of color, right? They mean something, right? These horizons don't just spontaneously appear for no reason at all. So what are the 6 major soil horizons? And also, let me just say, everyone, that this is the beauty of this. It's a very simple classification. There are only 6, but then it certainly gets much more complicated when you start looking of variations across different climates. But these are the 6, right? There are 2 surface horizons. So the 2 surface horizons are these ones up here, the O horizon and the A horizon. So an O horizon is easy to remember because the O stands for organic, right? So this is a horizon that is made up of fallen leaves and partially decomposed organic material, living material, organisms, and so on. So if you're walking around the Everglades of Florida or the swampy marshlands of Louisiana, for example, you will undoubtedly be treading on an O horizon, right? To be an O horizon, the concentration of organic matter has to be a certain percentage. We're not going to worry what that percentage is, but an O horizon is the most organically rich horizon, right, at the surface. Okay, the next horizon down is the A horizon, and this agriculturally is the most important horizon. So this is what we tend to think of as topsoil, all right? If you go down to your local Callaway's or Home Depot nursery and you need some soil for your pot plant, you're getting a combination of a little bit of O, but you're probably getting an A topsoil horizon with some organic material mixed in. So this is what we refer to as topsoil. It includes organic material, so the decomposition and the incorporation of broken down and incorporated organic material from the top. This is a word I just want you to be familiar. Humus, H-U-M-U-S, all right? That's not the stuff that you eat. That is the partially decomposed organic material. The A horizon also includes sediment, but that is the topsoil. That's the material in which we grow our crops, right? So there are 2 surface horizons, O and A. We then come to the 4 subsurface horizons, okay? This one here is unique to certain regions. The E horizon is a subsurface horizon. So this is a bleached horizon. It's a white bleached layer. It's called the zone of leaching. So you can see that term over here, the zone of leaching. What is leaching? Leaching is when water infiltrates into a soil and washes out the material, right? Washes out the good stuff like the silts and the clays and the organic material. And what's left behind is a relatively infertile bleached horizon. So these occur in regions of high rainfall. You've got to have enough rainfall, and you've got to have a sediment or a soil profile through which that rainfall can percolate. So that's an E horizon. It's a washed out horizon of material moving downwards. Again, unique to certain locations, and I'll show you what those are in just a second. The most important subsurface horizon is the B horizon, right? This is what we generally refer to as subsoil, okay? So this is a horizon where you get the accumulation of anything that's washed down from the surface. So the accumulation of decomposed organic material, the accumulation of iron, aluminium, oxides, and so on. Okay, so that's a subsoil zone of accumulation. The last two, let me go to the bottom one here first, because this is the straightforward one. The last two are the R horizon, and the R horizon is just bedrock. Okay, so that is an impenetrable layer of non-broken down bedrock. Okay, the C horizon, okay, the C horizon is potentially a little confusing. So let me just clarify the C horizon. The C horizon is what we call parent material, okay, PM, it's parent material. And so this is the material in which the soil forms, okay? It's the material that is exposed at the surface, and the soil then begins to develop in that material. Now, one of the reasons why it's potentially confusing is this, right? The parent material can be one material that is derived from the underlying bedrock. In other words, you can have a bedrock layer that is beginning to break down and weather, and that becomes the parent material, partially broken down mineral grains, right? So we see that a lot around here. So we've got limestone. We've talked about limestone already in Texas, and we've got a lot of limestone exposed at the surface. When that limestone breaks down into small bits and chunks, we get soils developing in that limestone, right, from that parent material. But the parent material can also be to material that has no resemblance to the bedrock. And that material is when sediments are laid down by rivers or by wind or by glaciers, for example. So you can have, and this can be a recent flood, but you can have material that's laid down through the geologic past by large floods. Right? So you can have a river can burst its bank and lay down 2, 3, 4, 5 feet of sediment, and that can be the parent material. The soils can develop in that material. And so what that leads to, everybody, is a classification for two types of soils, broadly speaking, right? We get one type of soils that we call residual soils, and the second type of soil we get is called transported soils. Residual soils are soils that develop on site from the broken down bedrock. In other words, the parent material is delivered from the bedrock lying underneath. Residual soils, right? Transported soils are soils that develop in material that has been transported from elsewhere, rivers, wind, and ice. So let me just stop there and see if there are any questions. Make sure everybody's happy with that. So 6 horizons and 2 broad different types of soils, residual soils and transported soils. Does that make sense? All good?
Transported.
Janira, say that again.
Can you explain transported one more time?
Yeah, absolutely. So you may have an area, let's say we're looking, and I'm looking down here, this is an area, and it's sitting on limestone, right? And you might have thin soils developing on this limestone. Those may be residual soils. I'll put a capital R there. And then let's say you have a large river somewhere else, and that river brings in a big deposit of sediments, right? Flood sediments. Let's say that's 2, 3, 4 feet thick, okay? The soils that develop in these transported materials by the river would be a transported soil. That can be sediments, Janira, that's laid down by wind. It can be sediments that's laid down by glaciers. My point is that the parent material is material that has been transported and deposited somewhere by another process. Does that make sense? Make more sense?
So is the parent material the transported soil?
Yes, the parent material is the transported material, and then the particular profiles can develop in that soil.
Okay, that makes sense.
Yep. Good question. Okay, so then let me show you and talk very, very briefly about the 2 most important soils that we have, right? So soils are classified. There are 12 different types of soils, very, very broadly speaking. And again, soil complexity is enormous, but at the very, very basic level, the kind of 35, 40,000 foot level, there are 12 different types of soils. And I'm just going to introduce you to 2, right? Our 2 most important soil types. So this is the first most important soil type, and this is what it's called down here. It's called a mollisol. The sol is Latin for soil, and the molly is Latin for soft, okay, soft or fertile. And these soils are in the United States, and we're just going to focus on the US here, these soils are the rich, fertile soils in which really agricultural wide-scale farming occurs, right? So anything that's brown on this map here that you see of the lower 48, the darker the brown, the greater the area that's covered by these mollisols. So you can see that when you look at the Midwest over here, right? When you look at this region here, right throughout the Midwest, where it gets darker and darker, those are the soils that we grow the majority of our intensive crops like corn, for example. They are characterized by a dark, rich A horizon. Now, you may look at that and say, well, hang on a second, that's a dark gray or a black horizon, and that must be an O. No, it's not. It's an A horizon. An O horizon is really sitting under forest layer or swampland where you get an incredibly rich organic content. This still has organic material in it, but you can see the scale down here. This is at least 2 feet of rich, fertile topsoil. About 25% of all of our soils in the United States are mollisols, and they're characterized by this thick, dark A horizon over a B horizon. If any of you are from Iowa, Kansas, or Nebraska, and I'm sure you are, you would be familiar, or you should be familiar with mollisol. So this is a very typical idyllic scene in Iowa, and you see big corn. These would all be organic, rich mollisols. Okay, make sense? So that's the most important, that's agriculturally, economically our most important soil. This is our second most important soil, at least in terms of agriculture and I suppose geographic coverage. So these soils are called ultisols, U-L-T-I-S-O-L. Again, sol meaning soil, ulti from the Latin ultimus, meaning these are the ultimate soils. And what that means is that these are soils that are old and have been leached, okay? They have had a lot of rainfall on them, and that rainfall is infiltrated through that soil and washed out a lot of material, leaving behind, and here it is, leaving behind that E horizon. So ultisols must have an E horizon, okay? So what you see on this diagram over here, this is a thin A horizon, and here's a washed out E horizon, and here's the B horizon here. But this is absolutely the critical distinguishing characteristic of ultisols, right? They are well drained, well washed out, lots of rainfall washing out all the good stuff. They're slightly acidic, but they're highly leached. And you can see here geographically where they are. Anything in greens and blues are ultisols. They're not nearly as fertile as the mollisols. What do you think we grow down here? What's a big crop over here on the coastal plain of the United States? Anybody think of a couple of crops that we grow over here?
Well, you got peaches in Georgia, and then if you go to Florida, there's lots of citrus and stuff. I know that's not in the circled part, but
yeah,
those are pretty like rainy areas and whatnot.
Yeah, okay, so citrus down south, good. Let's come back, let's just look at Mississippi, Alabama, South Carolina, North Carolina, and Georgia. Incidentally, these soils are all very, very sandy soils. So they've got very high infiltration capacities. They're old marine sediments. So they're very sandy soils. So they're transported soils, genera. And they're in the southeast that gets lots of rainfall, which is why they're so well leached.
What about the cotton belt?
Thank you, David. Cotton belt. Yeah, so cotton is one, right? Another one is tobacco. So it's not that you cannot grow in crops in here, but they're not nearly as fertile and are pretty poor relative to things like corn. Okay, so those two are the most important, at least in the United States, right? It's not that other soils are unimportant, but those two are the big ones. And here's an example of a tobacco field that has been cleared and prepared in North Carolina, just as a geographic. All right, so let's talk about the environmental issue here, okay? So the term here is, or the terms are soil degradation and land degradation. So soil degradation is a term that refers specifically to the decrease in the productivity of soils. Land degradation is a broader term that includes soil degradation and water pollution and deforestation and so on, right? Land degradation would include something like desertification, where climates are getting drier and drier, and you're getting the spread of deserts. So land degradation is a big, broad umbrella term. We're going to focus specifically here on soil degradation. And this is one of the general maps. It's kind of like the latitudinal diversity gradient map. And it's a map that shows the global status of human-induced soil degradation. Now, I'm not going to bog you down with exactly what very high severity means and low severity, but let's just keep it discussive here or descriptive. Anything in red or orange are soils of really significant concern, right? And the type of degradation includes soil erosion, and that's by far and away the most significant type of soil degradation. So that's the removal and complete loss of soils, either by wind or water. The soil degradation includes soil erosion. And incidentally, if we just want to put a number to it, when we talk about soil degradation, about 80 to 85% of all the world's soil degradation is attributable to soil erosion, right? So soil erosion is the most significant. There are other types of soil degradation, chemical degradation, physical compaction, and so on. But you're pretty safe to think of this as an erosion problem, right? So oranges and reds, high severity, and then the browns are moderately severe. So what do you notice here about this map? What jumps out at you? If we're just thinking about soil degradation dominated by erosion.
You had talked about the Midwest being like viable for our crops with corn, and it looks like they are more susceptible to erosion.
Yeah, that's a really nice observation, right? So you look at the Midwest. Okay, now this doesn't mean to say that the entire United States is, in dire trouble when it comes to soil erosion, right? Because there's low severity and moderate soil erosion we can take care of, and I'll make some of those comments towards the end. But yeah, that orange sector seems to coincide, right, with the mollisols and where a lot of agriculture in the US is done, okay? But certainly look at Southeast Asia, right? When you look at China and South Asia, Southeast Asia, Southern Africa, many parts of the world are in real trouble here when it comes to soils, okay? And part of that is linked to deforestation. Remember, when you're cutting down trees, you're exposing the soils, and a lot of that is running off. So I know this looks like a really dramatic map, and it is. It's supposed to be. So soil degradation goes from what we call light, right? So this would be light degradation. I took this photograph in a farmer's field in England many years ago. We've got a little bit of snow melting there, and you can see where these trees are. Some water is collected and is running down the slope, and it's cutting little channels. But this farmer isn't losing catastrophic amounts of soil, right? Part of that comes through runoff by erosion. Part of it comes through just the physical power of raindrops, right? And this is also often overlooked. Most people think soil erosion is just when you get water collecting on a surface and cutting channels, but raindrops and rain splash impact is enormously powerful in dislodging material and causing soil erosion. So for example, if we just look at the right-hand side here, so this photograph here is a photograph, this also takes me back many years. I had a student, when I taught in North Carolina, I had a student who was interested in erosion, as most people should be. And for his thesis, he went around, and this is a tobacco crop, and he went around after rainstorms looking at how much soil was being splashed onto tobacco crops and washing that soil off and measuring it. And you can see how cratered and pockmarked the surface here is. And it's just extraordinary how much soil was lost as a result of rainstorms in North Carolina under tobacco. So we have soil degradation that is light, and then soil degradation and soil loss that is not so light, right? So here we have catastrophic erosion down a much larger channel system. This is in central Spain, okay? It is important to appreciate that soil erosion is also a natural process, right? It's really important to get that out there because, so this is geologic erosion, right? Humans are not impacting this really in any significant way, right? So there's natural climate change, there's natural species extinction, there's natural soil erosion. And so we've got to acknowledge that what I'm talking about is human activities and what we're doing, like species extinction, like deforestation. What are we doing to change the climate? We are doing things to accelerate soil erosion, right? Soil degradation. And that's what the environmental issue really is. So when we look at the human activities and how they relate to soil degradation, this is what it pretty much comes out to, right? It's a fairly even spread when we look at the worldwide impacts of humans on soils. Agriculture clearly is a dominant one, deforestation as an act in and of itself, and overgrazing. Those three are the big, 90% plus of all erosion and degradation worldwide is due to overgrazing, too many cattle on an area, and they overgraze the crops and the grass, and those soils get exposed and erode, deforestation, and then agriculture, broadly speaking, right? Remember, everyone, when we talked about food, and I showed you that diagram in chapter 2 and asked you that on the exam when we looked at the area under cropland and the increase in population, right? And the fact that we have to farm smaller and smaller parcels of land, okay? This is in China, we're pretty much tapped out, right? When it comes to where we can go, okay? So these are rice paddies where they have this very unique terracing system. But as I made the point then, and I just want to make the point now before we go any further, we don't have hundreds of thousands of hectares of, pristine mollisols just waiting to be plowed. Okay, again, let me take a quick break there and see if you've got any thoughts or comments or questions before we get to answer this key question. How much soil are we losing? All good, everyone? All right. Okay. So let me take a step back here and just make a comment globally, and then I'll focus back in on the US, right? So if soil degradation is a significant environmental concern, and I would argue that it is, and if soil erosion is the most important part of that, how much soil are we losing, right? And is it significant? Okay, so here is, I think, a pretty startling estimate that was made a few years ago from a study that was done on worldwide soil loss, looking at rivers around the world and how much sediment is being transported, as well as looking at agricultural lands in a number of countries around the world. And this is the startling estimate, right? That an area the size of China and India combined has been severely degraded in the last 60 years, right? So coming out of the Great Acceleration, moving through the 1950s and 1960s and the ramping up of the Green Revolution and nitrogen fertilizers and so on, the downside to that is that we really have degraded enormous areas of land that are increasingly difficult and expensive to try and rehabilitate, right? When you lose soil, it's gone. And when it's gone, there's not a whole lot you can do about it. So that's the global picture, right? In the US, we certainly, as I think when you looked at that land severity map, we certainly have a soil erosion issue. I like to start here with this diagram because this is a region you'll probably recognize, right? So this is the Mississippi Delta. Okay, so here's the great city of New Orleans over here. And this over here is a gigantic sediment plume coming out into the Gulf of Mexico. But as you look down here along the Gulf, you can see several of them, right? This is following a large series of storms about a decade ago. And all of this sediment that's moving into the Gulf of Mexico basically represents our agricultural potential, right? This is, the majority of this is sediment that is running off agricultural fields, and the majority of that is coming out of the Mississippi drainage basin, okay? So what I want to do here, everybody, is address this question of how much soil are we losing, and then address whether it's significant. And let me tell you what's coming up in the exam on this topic. It's kind of like the calculations with the wind turbines. I'm going to ask you to be able to do a calculation, and the calculation is simple and straightforward, and it addresses this question. Does this particular farmer or does this country have a soil erosion problem? All built around this question, how much soil are we losing? Okay, All right, so here's the diagram. It's another one of these little multi-axis busy diagrams. So let me explain what is going on here. So this shows erosion on US croplands by year, right? From 1982 to 2012. Now, let me make a couple of quick comments about that scale. So the US Department of Agriculture and the Natural Resource Conservation Service, a bunch of government agencies, every 5 years, pull together data on what's been done in the research, and they assess the state of our soils. So this is a 5-year project, okay? So you're sitting here probably wondering, well, why does this only go up to 2012? Well, they were late in 2017 and 2018. Everything started getting delayed, and then of course COVID hit, and so we are now almost 10 years behind, right? But having said that, what are we looking at here? So this axis here is how many billions of tons are we losing off our croplands each year, in billions of tons. And this scale relates to these vertical columns. And I've broken the vertical columns out here, everybody, in terms of how many billions of tons are we losing by wind erosion, and how many billions of tons are we losing by water erosion, right? So this is the 5-year soil erosion by wind and water. And then this scale on the right here is how many tons per hectare per year, okay? And that's what the red diamonds are. In other words, when in 1982, when we lost 3 billion tons of soil in total, that equated to about 17.5 tons per hectare per year. Okay, so what do you notice? And remember, a hectare, let me just again contextualize a hectare, because this is the important unit of measurement. I've made a comment on this in forests. A hectare is 100 meters by 100 meters, right? So a hectare is basically 2 acres, a little more than 2 acres. Or if you're a sports person, it's 2 football fields. So there's 1 Amon Carter, here's 2 Amon Carter. That's what a hectare is. So what do you notice in terms of erosion on US croplands year by year, or at least every 5 years? What's the take home here? What do you think? Good news or bad news?
It's decreasing.
Okay, Catherine, it's decreasing. So yep, from 3 billion tons to about 2 billion tons, okay? All right, big check, that's good. So we've reduced soil erosion by about 1 billion tons per year, or from a rate of about 17.5 tons per hectare per year to about 11, right? This is one number I would like you to remember, 11 to 12, right? 11 to 12 tons per hectare. Just kind of park that in the back of your minds for a second, okay? So let's take that as the current average rate of soil loss in the United States, 11 to 12 tons per hectare per year, okay? Right? What does that mean, okay? Is that important or not, right? So I've tried to summarize this in this little diagram just to give you a context here. So this shows erosion. This is water erosion in the US, right? Compared to China, right? Water in the US compared to China. So let me just go back a second here, right? So what I'm going to do here is I'm looking at this 11 to 12 tons per hectare per year, okay? The majority of that is water and some of that is wind, right? So when you look at the US, now let's just look at the top right-hand one diagram here. I need to find my mouse real quick. Oh, it's a sleepy little computer. Okay, sorry, let me go back a second here. I don't know where my annotating tool's gone. All right, so, oh, sorry guys, I've just seemed to have had there we go. Don't know why it's disappeared. All right, so let's just focus up on the top right-hand corner here, okay? This is the average on-site soil erosion in the US by water, right? Almost 7 tons per hectare per year. mg is a ton, a megagram, right? I said, remember the 11 till 12? About 7 tons is by water, just in the US, okay? If you do not have a soil erosion issue, right, you should be down here in about the 2 tons per hectare per year, okay? So that's the average rate of soil erosion under natural grassland conditions, right? So we can already see that in the US, our soil erosion is elevated. In China, on average, it's greater than 15 tons. Remember that first big map that I showed you, right? At 15 tons per hectare per year, you are depleting soil resources faster than you can replenish them. You are in trouble, is the bottom line. So again, just to give you context, in the US, we are losing between 11 to 12 tons per hectare per year by wind and water combined, right? Here I'm saying we're losing about 7. So of that 11 to 12, about 7 is water and something like 3 to 4 is wind, okay? Now, the big question, and here's where the calculation comes in, right? The question is that significant, right? Do we have a soil erosion problem or are we okay? All right, so hang in here, everybody. So this is my way of trying to explain this. So let's say we've got a hectare. So this is a farmer's field. This is 1 hectare, right? Remember, that's 100 meters by 100 meters or 2 football fields, just to give you a context, okay? And let's just say, I said, let's remember 11 to 12 tons per hectare per year. Let's just say 12, right? Right? If you are losing 12 tons or megagrams, 12 tons per hectare per year, do you have a soil erosion problem or not? Well, that depends, right? It depends on how much soil you have. So 12 tons would fill a dump truck, an average dump truck. If you were to be able to scrape 12 tons of soil off a field, it would fill an average dump truck, okay? What would that look like in terms of the vertical inches of soil? Okay, 12 tons coming off a field would only look like 0.04 inches of soil, right? That's all it looks like, 0.04 inches of soil. So every 12 tons coming off a field equates to a vertical depth of about 0.04 inches, right? If you lose another 12 tons, you've lost another 0.04 inches. Another 12 tons, another 0.04 inches, and so on. Okay, so the question is, if 12 tons, if we're using this as our benchmark, 12 tons per hectare per year of soil erosion in the United States, can we afford to lose 12 tons per hectare per year? So that really depends, as I said, on how much soil you have at the outset. And what this comes down to is something called the t-value, right? So I want you to appreciate what the t-value is. The t-value is what we call tolerable soil loss, right? Tolerable soil loss. It's how much soil you can afford to lose, okay? It's like your bank account. How much money can you afford to lose if you want to go to Las Vegas for a weekend on the gambling tables, right? Well, Bill Gates could probably afford to lose more than me, as an example, right? Same with soil erosion. If you're sitting there with a very thick soil profile, you can probably afford to lose more soil. Now look at these 2 definitions. These 2 are the definitions of what tolerable erosion is. And the US Department of Agriculture defines that as the t-value, right? So this is the t-value. I need you to understand what the t-value is. There's 2 definitions. I'll quickly read them and then just look at the subtleties in the difference between these 2 definitions. Let me quickly check the time. We're good. The first one is the maximum amount of soil erosion loss that is offset by the theoretical rate of soil development, okay? So if you're losing 12 tons per hectare per year or 0.04 inches and soil is forming at the same rate, then you're in good shape, right? So that's one way of defining the t-value. How much soil are you losing relative to how much soil is being formed? The second definition here has more of an agricultural focus, right? That is the maximum average soil loss that will allow continuous cropping and maintain soil productivity without requiring additional management inputs. Folks, what do you think is meant by additional management inputs? What does that phrase mean to you, do you think? How much soil you can afford to lose without requiring additional management inputs?
I guess it's just more like how much you can push it before it actually fails.
Okay, yeah, a little more specific. How much you can push it before you start losing soil at a catastrophic rate. From an agricultural perspective, management inputs really means application of fertilizer, how much more nitrogen, how much more phosphorus, how many more things can you do to the soil to keep the yield up, right? So what is the t-value? In the United States, the t-value ranges. Here is what it ranges between. It ranges between 2 to 11 tons per hectare. That is what the t-value is in the US, right? 2 to 11 tons per hectare, or 1 to 5 acres per year, right? Anything above 11 is considered excessive, non-sustainable soil loss, whether you're talking about having to put in more fertilizer or simply the rates at which soils fall, okay? So 2 to 11 is the range. Why is it a range? Well, it depends on how much soil you have, right? If you're blessed with 60 inches of topsoil, then you can afford to lose more. If you're only dealing with 4, 5, 6 inches of topsoil, your t-value is going to be much lower, right? So here is where the calculation comes in. How much soil are we losing? Okay, cool. We've got 8 minutes to get this done. That is plenty of time. All right. So I'm going to give you a scenario, okay? And I'm going to ask you to address the question, does this farmer have a soil erosion problem or not, right, in this scenario, okay? And just like the wind turbine calculation, everybody, this is simple and straightforward, but you need to know how to do it. So the first question is, how long does it take to build up an inch of soil, right? Well, we don't really know, to be honest. What we do know is it's extremely slow, right? It takes a long time for rainfall and the environment to break down material into smaller bits and pieces, and it takes a longer time for organic material to begin to decompose and get incorporated. In other words, it takes a while to build up A horizons and B horizons. And this bullet point here gives you a summary, a broad summary, right? So normally it takes about 500 years to build up an inch of soil. Folks, that's a broad average, okay? In the tropics, it can be much faster because you've got lots more rainfall to do that work, right? In drier, colder areas, it takes longer. But that's a decent average. I think the literature suggests that it takes about 500 years to build up an inch of soil. Okay? In other words, each year, we're building up 1/500th of an inch. Okay, so 1 divided by 500 gives you 0.002 inches of soil per year, right? Everybody should be happy with that. That's the rate of soil formation. How much soil do you need for a decent crop? Well, that depends on the crop, right? But let's assume that you need at least 6 inches of soil to be able to grow a crop, okay? Now, we've also said, so yeah, in other words, if you need 6 inches of soil, you need about 3,000 years to build up a reasonable topsoil, okay? So now what about the soil loss side of it, okay? 12 tons per hectare. If you're losing 12 tons per hectare, the dump truck, right, which is currently the average rate of soil loss in the United States. Remember, that is a vertical loss of 0.04 inches, okay? In other words, you're losing about 1/25th of an inch every year, okay? So in 1 year, you'll lose 0.04. The next year, you'll lose another 0.04, so it becomes 0.08. In another year, you lose another 0.04, and so on, until you've lost an inch, right? So 1/25th of an inch every year. Does that make sense? Right? In other words, 1 divided by 0.04 is 25. it takes 25 years to lose an inch of soil. Okay, now you can immediately see from this example, if it takes 25 years to lose an inch of soil, right, and 500 years to build an inch of soil, you've got a soil erosion problem, right? And how do you calculate what that soil erosion problem is? Well, you can do it one of two ways. You can say, well, it takes 500 years to build an inch of soil and 25 years to lose an inch of soil, right? So 500 divided by 25 is? What's 500 divided by 25?
20.
Yep, it's 20. You're losing soil here 20 times faster than it's being built up, right? You can do it by the inches. 0.04 divided by 0.002 gives you 20. Okay, so I'm going to ask you in the exam, does this person have a soil erosion problem, right? So since 1/500th of an inch is being built up naturally, okay, soil is being depleted 20 times faster. Now I'm going to give you some different numbers, okay, but I've got to give you that information, right? And all you have to do, I can't stress this enough, all you have to do is take the rate at which soil is being formed divided by the rate at which it's being lost. That's all you got to do, okay? So let me stop there and see if anybody has any questions or issues with that. Does everybody see that? Do not feel shy or embarrassed if you don't. So I've got to give you the rate of soil formation and the rate of soil loss, right? And I'll change those numbers up. In other words, I will say to you, this farmer's not losing 12 tons per hectare, but they're losing 6 tons per hectare, or 0.02 inches. It's not taking 500 years to build, it's taking 100 years to build, right? Whatever the numbers are, I will give you those numbers. Okay. So this is the summary diagram, right? In the US, how much soil are we losing? So what I've done is I've taken all the data from the US Department of Agriculture and plotted it like this. Anything in yellow are areas that are losing soil at rates that are 1.5 times the t-value, right? 1.5 times the t-value. Anything in dark brown, we're losing soil at rates that are twice the tolerable rate. So you can see there are large parts of the US where there's no real soil erosion issue, but there are other parts where we've got a significant soil erosion issue. Soil is being lost, right? Look at West Texas. Soil is being lost here at rates that are generally 1.5 to 2 times the allowable or the rate that we can afford to lose, if that makes sense. Questions, everybody? So what I want to do here is, let me stop there. We're almost out of time. I'm going to take just about 10 minutes on Thursday to talk, just to recap this and then talk about what can be done. And what are we doing? Why have we gone from 3 billion tons to 2 billion tons? And then we will start with water quality. So let me stop the recording. And as always, I will hang around to see if you've got any questions.
Thank you.
You bet, everyone.
Thank you.
Thank you.
Yeah, you got it.
Thank you.
Have a good day.